training about power factor and harmonic distortion. It will be in two parts. The content of this complete training is, first of all, the power factor and cosinus phi. What is really the difference? After this section, we have a small Q&A. If you have any questions, you can ask them at that end. And the second part is going about harmonics, harmonic distortion. What is the effect? What kind of solutions there are for drives? And at the end, we have also the delta power quality solutions. And after this part, we have also a second Q&A. You can also visit our YouTube channel afterwards. Then you can see also this recording. Maybe you can, you forget something, but you have always a backup afterwards. And you can find also a lot of information about our products in our download center. First of all, power factor and cosinus phi. Power factor and cosinus phi are not the same. Some statements that are all true. Here the same, the power factor is, if the power factor is 1, then the cosinus phi is also 1. If the power factor is lower than 1, the cosinus phi can still be 1. If the cosinus phi is smaller than 1, also the power factor has to be smaller than 1. In short, power factor is always smaller or equal than cosinus phi. You see, it's a little bit confusing. I try to explain it in the next few slides. First of all, if we connect a resistive load to our normal power supply, the main supply, we have a sine wave form for the voltage and the current, equal shape. Current and voltage are in phase, no displacements between them because it's a resistive load. In this case, cosinus phi and power factor are exactly the same. If we now connect an inductive load to the normal main supply, we still have a sine wave form for the voltage and the current. The current and the voltage are not in phase. The current is always lagging on the voltage. This displacement is called phi. In this case, the power factor is still equal to cosinus phi, but they are smaller than 1 because they are not in phase. The angle has influence on the power, the real power. The displacement angle will create 3 types of power. You have the real power, the reactive power, and the apparent power. Energy companies don't like the reactive power because they have to deliver the apparent power to our main supply. And we are only paying finally for the real power. So the less reactive power we have, it's better for the energy company. But is that also for us? To remember it more easy, we can use the beer mug analogy. Active power is the beer. The reactive power is the foam. Total is the apparent power, is the total of two of this. The power factor is the active power divided by the apparent power. This is still true. Now we go back to our frequency drive. Here you see a diagram, a block diagram of a frequency inverter. In the front, we have a rectifier bridge connected to the main. We have an IGBT part, inverter part connected to the motor. And in the middle, we have normally a DC link. At what signal is going to the motor is a pulse width modulated DC voltage, because we have still the DC in the middle. This is controlled by the control unit. So this is a diagram for a non-linear load, and that will make the difference. Here you see the current of at the left you see the current of a three-phase inverter connected to the main supply. The voltage is still same sine wave. The current don't look at all at the sine wave. At the right, you see the current of a one-phase inverter. So that's already, it's even more not looking like a sine wave. In this case, the power factor is not the same as the cosinus phi anymore. The power factor is influenced by the harmonic distortion of the current, the THDI. So, a small conclusion, cosinus phi and power factor are often confused. Phi is the phase angle between the voltage and the current, so the cosinus phi is only related to that angle. The power factor is the ratio between the active, the real power, and the apparent power in the circuit. The true power factor also takes in consideration the harmonic distortion of the current with non-linear loads. A sine wave voltage with a block form current still can have a cosinus phi of 1, but the power factor is lower than 1. Cosinus phi is also called displacement power factor. Does anybody has a question? No? Then I go to the next part. What is really harmonic distortion? Because we saw that the power factor is influenced by the harmonic distortion. Harmonic currents, harmonic distortion is always caused by non-linear loads. That we have seen with linear loads, we have the same shape for the voltage as for the current. So then we don't have any problems. With non-linear loads, we have a voltage what is still sine wave, and the current don't look at all at the sine wave. Some examples. Linear loads, resistors, capacitors, inductors, motors, transformers, directly connected to the main supply. Non-linear loads, then you can speak about soft starters, servo drives, all kind of power electronics, also lighting, LED lighting, for example, or tube lighting is also a non-linear load. The current is completely different from the shape from the voltage. With Fourier analysis, you can calculate the harmonics in the different levels. It is the fundamental is the 50 hertz. In Europe, it's the 50 hertz frequency. And then you have the first, the second, the third, the fifth, fourth, and the frequencies. Altogether, they form the shape of the current. You see here in red and all different other colors, the different levels what are calculated in harmonic distortion with Fourier analysis. To see the simple single phase AC drive, you see here the voltage on the DC bus. It is not really straight. For the three phase, it's more straight, but the current is completely not in the shape form of sine wave. Output of the input voltage is also influenced a little bit due to this kind of currents. It's depending on the main supply itself. At the right, you see an example of a three-phase inverter frequency drive. As we showed before, the voltage is sine wave, the current totally not at all. If you do the Fourier analysis, you can calculate all different levels of harmonics. For example, here an example you see for a three-phase, one-phase AC drive. First, you have the fundamental, of course, the 50 Hertz current shape. After that, you have the third harmonic. That means 3 times 50 Hertz, 150 Hertz frequency. After that, the fifth harmonic, 250 Hertz, the seventh harmonic, 350 Hertz, and so on. Here you see the difference between a one-phase frequency inverter and a three-phase frequency inverter. You see the difference in the harmonic orders. The one-phase inverter has all odd harmonic orders. In the three-phase inverter, you miss some of them. For example, you don't see the third and the 9th and the 15th order. That's always. You even don't see the even harmonic orders in the frequency driving input currents, because the average of that one is 0. We spoke already a little bit about the power factor, and that is the power factor. It is influenced by harmonic distortion. Here you see the calculation of the THCI, more or less, and the relation between the cosine phi and the different powers, the real power, apparent power. The difference between this part is the D. It's the influence of the harmonic distortion of the current on the cosinus phi. And that is basically the power factor. How to calculate the total harmonic distortion? You have to do, what you have to do is to, first of all, you have to measure the values, the different harmonic orders, because it is not easy to do that by calculation of with Fourier analysis. That's a really mathematic exercise. And we can do it easy to measure it with a power meter or a power device. When you have the different orders and the different currents, you directly can calculate the THCI percentage, what is available on the main supply. DU, of course, the voltage will be also can have an harmonic distortion. But this is depending on the impedance of the total system. And of course, the distortion of the current. So the voltage is depending on the harmonic current distortion, but also on the impedance of your total system. Things to remember: THCI currents, harmonic distortion currents, can overload the transformer, cables, and other components and supply side. Voltage harmonic distortions can disturb sensitive equipment. So it's depending on the product itself, if it can be influenced by harmonic distortion of voltage. Also, frequency of the harmonics, the higher harmonics, can cause a resonance in the capacitor bank if they are used in the factory. Harmonic currents can cause extra losses in cables and also in main transformers. Some standards. There are two standards known. The one is the European one. It's the EIC EN 61800-3. Here you see also the table. In this table you see also that for inverters the THCI has to be lower than 48%. And the most common, what you see in all kind of documents, is the IEEE 519. And this is a recommendation. It's not a standard, it's a recommendation. And it gives a general recommendation for THCI lower than 5%. What are the effects of harmonic distortion? One of them is the overload of the neutral. You don't see with three-phase, there's three-phase inverters, it's more or less no problem. Because the average in the neutral, when you have a neutral, is 0 in that case. And the most important for the neutral in this case is the third harmonic. But when you connect a lot of one-phase inverters, for example, to a three-phase net divided over the three phases, and even if the currents are all the same, you still have an overload in your neutral. Because if, for example, you see the third harmonic causes the trouble. It is in the third harmonic is not 0 in all cases. That means for a small calculation, in the fundamental in each phase is, for example, 10 amps. The third harmonic is roughly 60% of the fundamental. It's 6 amps. That means in total, you have to add all three phases. It will be in neutral, more or less 18 amps. So that's already more than the fundamental. Of course, this is not only with the third harmonic, but also for the 9th, 15th, 21, and so on. Another effect of harmonic distortion is, of course, unexpected tripping of safety devices. Safety devices normally, most of them have a B-metal inside, and harmonic distortion of currents can heat it up. So the device can trip when it is not needed, not required. Another effect can be the overloading of the cable. Reactive currents of harmonic distortion of the current are higher frequency and they are going to the outside of the cable. So that means you have a different density in the cable at the side and in the middle. The density in the middle of the cable in the wire is lower than at the outside. That means your cable is getting hot. It's heating up cables. Overload of transformers. Normally a transformer will be dimensioned on through sine wave voltage and currents. But we have seen that harmonic distortion currents have influence on the total power, what is really needed. So if you want to have the proper calculation, you need to design the transformer a little bit bigger. And that is more expensive. Capacitor banks. Because the higher frequency, you lower the impedance of the system. And this causes higher currents. And if sometimes also you destroy the capacitor banks. If you have a mixed system with inverters and direct line motors, you get extra heating of the motors, because the harmonic distortion of the voltage of the current, I must say, can create higher temperature in the motor itself. Also, when there is an harmonic distortion of the voltage, when it is really tough, the speed of the motor can also change. Solutions. Of course, there are different kinds of solutions for drives available in the market. What can we do? We have 5 different solutions for reducing the harmonics in drives. You can use AC or DC reactors. We can use multi-pulse rectifiers, passive filters, active filters, and of course, active front end. AC or DC reactor. DC reactor means that there is a reactor placed in the DC of a frequency drive. AC reactor or line reactor is in front of the frequency drive. Without any reactor, the THZI is roughly 80 or between 80 and 90%. With a DC reactor, you can lower it directly to lower than 48%. It's depending, of course, of the impedance of the reactor itself. But with a 3% reactor, you are lower than already the 48% what is required. The same for the line reactor. If instead of a DC reactor, you can have also an AC line reactor. With the same impedance of 3%, you have the same THZI level, more or less. Of course, you can play a little bit with the impedance of the reactor itself. Our drives have an built-in DC reactor above 37 kilowatt, and that is a 3% impedance reactor. But if you should change that to a 4%, for example, the THZI will be lower. With the 3%, we are at roughly 43% THZI. With the 4% reactor, you can go down to 38%. Of course, you can take a high impedance reactor inside the drive, but there is always an end on it. There will be also a voltage drop over the reactor. That means that the output voltage will also get lower if you go too high. You can have also a combination of DC and AC reactors if you want. If you have a built-in DC reactor of 3% impedance, and you use also an AC reactor of 3% impedance, the THCI will go down till roughly 30%. That means you have a difference of 13% THCI compared with the DC reactor. Multiple pulse rectifiers. A standard frequency drive is a 6-pulse rectifier, it's called. It has 6 diodes in the drive itself. But for larger powers, you can have also systems that parallel the diodes itself. So that means instead of 6 diodes, you have 12 or 18 diodes in the system. 12 diodes means 12 pulse rectifier. So you can play with it. If you have a phase shift transformer in the beginning of, for example, 30% for a 12 pulse system, you can reduce the harmonic distortion of the 5th and the 7th harmonic a lot. So that means your THDI goes really down. Standard with the 6-pulse rectifier, in our case, in our drives, we have a system of 43% more or less. With the 12-pulse system, you can go down to, in our case, 12%. If you have a higher impedance, you can go down to for 30 or 10% in that case. And if you look to our drives, for example, the G and the H frame sizes of the CP can be used in a 12-pulse system because we have a double input rectifier. That means we have 12 diodes in the system. Normally they are parallel, connected parallel, but if you have a transformer, a shift transformer available in your system, or you create a system with a shift transformer, you can lower down the THCI till roughly 12%. An example how it looks like. Here you see the currents of a 12-pulse system. In red, we have the star output of the shift transformer. And yellow, we have the delta output of the transformer. The white one is, for example, the total at the input of the transformer. So that means, yeah, more or less, in this case, the THCI of the star and the delta was each roughly 33%, and the total has an harmonic distortion at the input of the transformer of roughly 12%. Be aware, this kind of constructions normally is only done for large powers, because otherwise this makes no sense to use a special transformer for this kind of applications. And the transformer is always dedicated to the drive itself. Passive harmonic filter. It's a low pass filter. And that is a filter with an inductance and capacitors. And with this kind of filters, depending on the values of the capacitance and the inductance, you can lower the TH down between 5 and 60% at full load. These kind of filters are always calculated at full load applications. You see when your load is going down, you get a difference, of course, in your THCI, and then the total THCI can also be different in that case. but roughly from 50 to 100% load, you have more or less the same THCI, between 5 and 16%. It lowers the fifth and the seventh harmonic most of the time, but sometimes also the higher ones a little bit, so to lower the complete systems. It can be used in combination with frequency drive or other type of nonlinear loads. Active filtering, basically it is the same as for a passive filter. It is using capacitors and inductors in the filter itself, but what the difference is that an active filter is continuously measuring the current form, and it also detects what kind of harmonics are on that current. And depending on the level, they inject the more or less capacitance or inductance in the system, so they can lower down the THCI till approximately 3 to 5%. Active front end. Of course, an active front end is or can also be used in combination with frequency drive. Active front end is not more than basically an inverter in the direction of the main supply, but because an inverter has a DC voltage output, you have to use a reactor in the direction of your main supply, or sometimes also, to reach the THCI level at 5%, you have to use an LCL filter in that case. A summary and small overview of what the influence is, and also, of course, what the cost is. For lowering the THCI till 35%, you can use a DC reactor of 4%. In our drive is already built in 3%, so we are going down to 43%. It has a good EMC performance also. It's also nice to have. And it is not too cost effective. The second one will be the passive filter. Passive filter has roughly the same price as a frequency inverter, normally in that range. You can go down with the THCI till lower than 5% in some cases, and also, most of it is lower than 16%. It has a good cost effective, lower than 100 kilowatts. At this moment, it's going up already to 160, 200 kilowatts. Then it's cost effective. There is a point of course, what is very important, because we are using capacitance and inductance. You have always a risk of resonance if you use a lot of these kind of filters in one system. The third one is a 12 pulse system, and then you have to go up to 400 kilowatt or higher. You need a special transformer, so it is not really cheap, but you have a good performance, and you can go down to roughly 12% of the THCI. If you go up to an 18 pulse system, for example, then you have 18 diodes in the beginning. You can also go lower down than 8% or sometimes lower. Active front end, you can reach the THCI level lower than 5% if you use an LCL filter. You can also regenerate and use it as a regenerative drive in that case, because when you have an application like a crane, energy comes back to the DC bus of the drive itself, and you can regen that back to the main supply. So in that case, it's also effective, not only for the THCI, but also for using less power. And the last one is an active filter. Of course, you can go lower than THCI than 5%, but it is normally used not for one drive. It can be, but then it's very expensive. But normally it's used for a complete installation at the incoming of the main supply. Now, the Delta solutions, what we have, what we can provide. Of course, first of all, we have power meters. As mentioned before, you have to measure the harmonics before you can use a kind of filter, that you know what your level is and where you want to go. We have 3 different types. We have a panel mount version, DIN rail mounted, and also multi-circuit type. In combination with DI energy program, we can also use that to measure, to see what's happening in your complete factory. The panel mount version, if you use the C530E, you can measure directly the individual harmonics up till the 31 harmonic level. But also you can measure directly the power factor and also the different powers. The inner mounted type, there is a difference between the DA510 and the DA530. And the difference is basically you can measure the individual harmonics only with the 530 in that case. And we have a multi-circuit type version. It can also measure directly the individual harmonics. Filtering, what we can provide for harmonic distortion filtering is a lot of different types. We start with the regenerative unit. It is not really reducing the harmonics a lot. What you do with this one is saving a lot of energy. You don't burn all the energy in a brake resistor. But you bring the energy back to your main supply. Our REC 2000 has a built-in reactor. Otherwise, you cannot connect it directly to the main supply. But the current, what's coming out in the direction of your main supply is not sine wave form. So you create the disturbance already on your main supply together with the drive. But because you are using in combination with frequency drive, the total harmonic distortion will go less a little bit. This is the wiring diagram. REC 2000 directly connected to the DC bus of the frequency drive. And you can have an AC reactor for the drive, of course, but it's not always necessary. Build up type number. It goes up to maximum 55 kilowatt, and then you can parallel them, for example. Active front end. We have seen it is more or less a double drive what you have. It is an IGBT what is connected, a controlled rectifier with IGBTs. It is not diodes anymore. You are using IGBTs in that case, and you have always to use at minimum a reactor to your main supply. If you use an LCL filter, the THDI can go down lower than 5% in that case. But it corrects also the power factor in the system. Here the wiring diagram. You can use an active front end for only one drive, frequency drive, but you can also connect more than one frequency drive or servo drive directly to that active front end. The only thing where you have to be aware of it is that the drives, what you are connected, have the same DC level, of course. Otherwise, you blow it up at the end. If you combine the standard AC reactor, what is delivered with the AFE, an LC filter, then you have basically the LCL filter complete, and then you go down lower than 5%. Type number overview, of course. You have to order the LC filter separately because it is not mandatory to have, but only for reaching the lower than 5%, it is really necessary. Otherwise, you cannot reach it. But you have also to order the standard reactor separately. New in our portfolio is the passive power filter, PPF. We have two different types. We have a version of a PPF that can be used to lower the THCI of the frequency drive lower than roughly 8%. And we have a PPF what can be used with the drive, and then it's going lower than 5% THCI. So it's a different version. The difference is, of course, the amount of capacitors and inductance in the filter itself. As I mentioned, the THCI will be only between roughly 40–50%, and 100% load will be calculated in that case. If you go down under the 40%, then the harmonic distortion will be a little bit higher. How it's built up, the part number. You see after PPF, we have the two different types. We have the S for the standard version, then it's roughly 8% THCI. And we have the P, high performance, the performance one, and then you go lower down till 5%. This reduction can only be reached with a frequency drive with a built-in DC reactor. Be aware of that, because then you are in the range of 40% THCI already for a standard drive, and with this filter you can go down to the requirements of 5 or 8%. If you have a drive without built-in DC reactor, you still can use this kind of filters, but then you cannot reach this kind of level. If you use the high performance filter in combination with the frequency drive without DC reactor, you can reach roughly 12–16% THCI. It's depending on the power. The next one is an active power filter, an APF. We only use this for large accounts because it is always difficult to tell people how it works, how to program it. And if you have to tell every time for one unit, it costs a lot of time. The active power filter is developed for compensating the harmonics, but it also compensates some of the reactive power itself. So it is also helping that one. It is for cleaning the grid, just so you don't use it for a simple frequency drive. You connect this kind of filters most of the time at the incoming point of your main supply. It can be used for unbalanced loads, and it compensates also reactive power a little bit. The current harmonic distortion will be compensated till the fifth harmonic. So then the level will go really down. And also this one you can parallel, for example. This is how the type number is built up, APF. Then you have only 4 versions in current. The 50, 100, 200 and 300 amps. And the last one, it's a static VAR generator. The difference between the APF and the SVG, SVG is compensating the reactive power. And by doing this, they also compensate, of course, a lot of the harmonics, but not at the same level as what an active filter is doing. That is basically the difference between the APF and the SVG. It looks like the same at the output. It can also be used for unbalanced load, but the harmonics, the THEI, will only compensate till the 13th harmonic. Type number overview, we have only 2 versions. In this case, the 300 kVA and also the 500 kVA. Also, you can parallel them. Summarize overview. It's depending, of course, what you want to do, what you want to change. You can use a type of solution, I must say. You can build in a reactor. In our frequency drive, we have a built-in DC reactor in a power range higher than 37 kilowatt. And the lower ones, there is not a built-in DC reactor at all. For the higher sizes, the G and the H frame, these 2 frames can be used for 12 pulse diode and diode bridge. Normally they are parallel connected, but if you have a special transformer, you can disconnect, of course, the both diode bridges, and then you can connect it to a 12 pulse transformer. The Reg 2000 is only for give energy back to the main supply. It does not compensate really the harmonics, but it is a more efficiency unit, more high efficiency unit. Instead of burning all the power in brake resistors, you can also put it back to the main supply. Then the next one will be more or less the active front end. Active front end it can be used in combination with more than one drive. It can be used for lowering the harmonics to the main supply, if you use that in combination with an LCL filter or an LC filter, in our case. But you can also use it for regenerative applications, like in hoisting, crane. Yeah, there are a lot of kind of applications where it can be used for. And it compensates also we have also correction of the power factor in the case. Next one is the PPF, the passive power filter. It can only be used for lowering the harmonic distortion of the current. 2 different types. One is going down to 8% roughly, and the other one is going down lower than 5%. And that is only in combination with the frequency drive with a built-in DC reactor. The next one, the difference, the APF 2000 and SVG 2000, it is both compensates the reactive power, can be used for load balancing, can be used in unbalanced loads. It is for lowering the harmonic distortion and compensates also the correction also for the power factor. There is a difference between the SVG and the APF. APF is basically compensates the harmonics till the 5th harmonic and the SVG only till the 13th. In that case, if you want to use it for the harmonic distortion compensating, the APF is a better choice. If you want to use it for a reactive power compensation, then the SVG 2000 is the best choice in that case.